We choose to go to the moon in this decade and do the other things, not because they are easy.
3, 2, 1.
But because they are hard.
In physics, impulse describes how much force is output over a given number of seconds. Mathematically, this is the integral of force with respect to time, or the average force multiplied by time. You might be thinking that this equation looks familiar. It is similar to the equation for work. Just how the amount of work done on an object equals the object's change in kinetic energy, the amount of impulse imparted on an object equals the object's change in linear momentum. Impulse is primarily used to describe collisions and propulsion. Let's consider a car crash as an example of a collision. The car's momentum doesn't drop to zero immediately. There's a force acting on the car for a certain, albeit very small, amount of time. The impulse the wall imparts to the car is the integral of the force of the crash for the duration of the crash. The impulse is, in this scenario, also equal to the change in the linear momentum of the car wall system, so it indirectly measures the change in the velocity of the system. Impulse can also act as a barometer for how high a propelled object will go or how far it will travel. Given two objects of equal mass, the one to which more impulse is imparted should fly higher. Unsurprisingly, we decided to study impulse through rocketry.
We launched 2 rockets. First up is the Apogee F10 with 75 newton-seconds of impulse and a 7-second burn. Afterwards is the Aerotech G80 with 130 newton-seconds of impulse and a 1.5-second burn.
Good thing you didn't call your dad back. Whoa!
Holy smokes.
Oh my God.
5, 4, 3, 2, 1.
It's clear the G80 is much faster. Just look at how quickly it leaves the frame. Remember hearing how long the F10 burned? It's a battle of force versus time. How do we tell which motor goes higher? We can find out maximum height by adding burn height to coast height. We know the impulse, burn time, and average mass of each rocket from their spec sheets. Given impulse and average mass, we can find the velocity at the end of the burn, and from there, average velocity during the burn. We can then deduce burn height from simple kinematics. Next, we use gravity to find coast time, which then gives us coast height. Adding this to burn height gives us the maximum altitude of each rocket. Of course, these numbers are off due to drag, but they reflect the central truth that the higher impulse rocket travels higher in the sky.
In the words of JFK, space is here,
And we are going to climb it.